Here's a reminder of how to do some calculations, simple ones, regarding the behavior of a gas. The first relationship we'd like to look at is the relationship between volume and pressure. And we remember from what we talked about in class that these two are inversely proportional in terms of their behavior. In other words, as the pressure of a gas increases, the volume it occupies decreases. It's in the opposite direction. As the pressure on a gas decreases, the volume that it occupies increases. That's why this inversely proportional, we can kind of think of it as reversely proportional. And remember, this is the equation that will allow us to do simple calculations of this relationship. The initial volume, VI, multiplied by the initial pressure, PI, should be equal to the final volume, VF, multiplied by the final pressure, PF. And so let's take a look at this word problem. Gas at 1 atmosphere has a volume of 50 liters. What is the new pressure when the volume is increased to 50 liters? So let's write down what we know just by reading the question. In other words, we know that the initial volume is 50 liters. It's right here. We know that the initial pressure is 1 atmosphere. It's given right here. Next, we are talking about a new volume, a final volume of 85 liters. And the question for this word problem is, what is the new pressure? What is the final pressure? Before we go with our calculation, we need to try to make a prediction. Take a look. You'll notice that the volume increased from 50 to 85. And what do we know about this inversely proportional relationship? If the volume increased, we make a prediction that the pressure will decrease. So let's take a look at that when we finish all the calculations. All right. And so let's just rewrite the equation. VI times PI should be equal to VF multiplied by PF. Let's substitute. 50 liters multiplied by the pressure, 1 atmosphere, should be equal to the final volume, which is 85 liters, and the final pressure, which we don't know, so we just write PF. Let's examine what kind of algebra we need here. How do we get rid of the unit of 85 liters? Let's divide both sides by 85 liters. And that way we can isolate the final pressure on this side. So we'll divide both sides by 85 liters. By doing that, we can cross out the word liters, and we're left with the units of atmosphere. And that is the correct unit for a final pressure. So at least in terms of units, we're correct. What should we do on a calculator? We see that we need to multiply 50 multiplied by 1 divided by 85. And if we go ahead and do that calculation, we realize that the numerical answer is 0.59, and the unit is atmosphere, because after all, liters canceled out with liters. Now let's take a look. Is this in fact consistent with what we predicted? Sure it is. When the volume goes up, the pressure decreased. It went from 1 atmosphere and decreased down to 0.59 atmospheres. The new pressure is 0.59 atmosphere. Let's continue to the next kind of relationship. The next relationship of gas behavior is the relationship between volume and temperature. And we remember from what we learned in class that volume and temperature are directly proportional when it comes to gases. In other words, as the temperature of a gas increases, the volume it occupies also increases. As the temperature goes down, the volume it occupies also goes down. In class, we learned that this is the equation to calculate that kind of relationship. So let's read the word problem. The word problem says, gas at 273 Kelvin has a volume of 85 liters. What is the new volume when the temperature is increased to 300 Kelvin? Let's write down the given. What is the initial temperature? The initial temperature is 273 Kelvin. All right. What is the initial volume? The initial volume is 85 liters. It's told to you right here. The new temperature, the final temperature, is 300 Kelvin. And the new volume, the final volume, is what we are calculating. And so this has to increase because the temperature also increased. Remember, this is a directly proportional relationship. All right. With that said, let's go ahead and calculate for the final volume. Take a look at this equation right here. To calculate for the final volume, you need to do cross multiplication. And in order for us to be quick about it, let's just understand that the final volume is equal to the initial volume multiplied by the final temperature, all divided by the initial temperature. All right. And so let's give this a shot. The final volume is equal to the initial volume multiplied by the final temperature divided by the initial temperature. All right. The final volume is equal to, let's keep an eye on our units, please. 85 liters is the initial volume. The final temperature is 300 Kelvin. And that's all divided by the initial temperature, 273 Kelvin. And so what units can cancel out? The Kelvin units cancel out. And the only unit left is liters. And that is the correct unit for volume. And what would we do on a calculator? Simply 85 multiplied by 300 divided by 273. And if you do that calculation, you'll find out that the answer is 93.4 liters. And if to be strict about the answer, since there were 2 digits in the correct answer, it would be something like 93 liters. Right? So let's see, is this consistent with our prediction? If the temperature went up, did the volume in fact go up? According to our calculation, it did. And so that's consistent with our prediction. Let's take a look at the third relationship. In this relationship, we take a look at temperature and pressure. And in terms of a gas, as the temperature of a gas increases, its pressure increases. And this should actually say as the temperature decreases, then the pressure decreases. In other words, this is a directly proportional relationship. And we learned in class that this is the equation that we would use for this kind of a relationship. Let's take a look at the word problem. Gas at 473 Kelvin has a pressure of 3.85 atmosphere. What is the new pressure when the volume is decreased to this should say the temperature. Sorry about that. When the temperature is decreased to 300 Kelvin. All right, let's take a look at the given. What is the initial temperature? The initial temperature is 473 Kelvin. That's given right here. What is the initial pressure? The initial pressure is 3.85 atmosphere. That's given right here. What is the final temperature? The final temperature is 300 Kelvin. In other words, it's decreased. What then is the final pressure? We need to find out. But what kind of prediction can we make? Since this is a directly proportional relationship, we can predict that since the temperature went down, the pressure will also go down. It will decrease. Let's use some algebra to solve for the final pressure. Remember, we're doing cross multiplication here. The final pressure is equal to the final temperature multiplied by the initial pressure, all divided by the initial temperature. So let's rewrite that over here. PF is equal to final temperature multiplied by initial temperature, all divided by the initial temperature. Let's substitute. And remember, keep an eye on your units. The final temperature is 300 Kelvin. All right, there it is, final temperature. The initial pressure was 3.85 atmospheres. It says it right here, 3.85 atmosphere. Divided by the initial temperature is 473 Kelvin. And what units can cancel out? You'll notice that Kelvin cancel out, and the only unit left is atmosphere, and that is the correct unit for measuring pressure. And so let's take a look. With 3 digits, let's find a 3-digit answer. 300 multiplied by 3.85 divided by 473 gives us an answer of 2.44 atmosphere as the final pressure. And so let's take a look. Did, in fact, the pressure go down as we had predicted? Sure it did. It went from 3.85, it decreased down to 2.44 because as temperature decreases, pressure also decreases. Now, using all of these lessons from today, please take a look at the problem set that was assigned to you and fill in the answers and submit through your Google Classroom. Thank you.